Welcome to this lecture. During the following minutes, I will talk to you about interlocking planks. But first, let me introduce myself. I'm Michael Blanc, and I'm working as a technical support and conception engineer for Bacacier. Bacacier is a French manufacturer of steel sheeting products used in both cladding, roofing, and decking. Bacacier is the third actor on the French market, holding 20% of this one. During this project, Bacacier was responsible for the supplying of half the samples and of the work package we are currently dealing with. Here is the plan we will follow during the lecture you are currently watching. After an introduction, where we will see why interlocking planks were developed, what possibilities offer such profiles, what is the current state of the art concerning the design procedures, and what are the typical problems for such profiles, we will see, in detail, what were the tests carried out during the GRIS project, and what were the interesting results of these tests. Eventually, we will have an overall look to the design method by calculation we built up to get the most realistic values regarding test observations and in accordance to the actual calculation approach of Eurocode 3 Part 1.3. Steel is a light, resistant, and competitive material. This is why it is so often used in the construction industry and, in particular, industrial and agricultural buildings. But traditional steel envelope products suffer of this cheap industrial image. To provide solutions for higher quality or premium buildings, architects asked manufacturers to work on solutions offering no upper ring fixing device and the flattest surface possible. This had to be done preserving the cost effectiveness and the convenience of steel products they lacked for industrial and agricultural buildings. They wanted the cheapest profile possible for their building to project the most upscale appearance. As you can see here, manufacturers' answer was to put on the market channel type profile with asymmetric edges. The inspiration here is clearly the traditional wooden cladding planks with a male edge and a female one, realizing, once assembled, a waterproof joint. Of course, the weight of such profiles is light compared to plain wood sections. Taking into account these sections are hollow and their steel thicknesses is generally between 1 and 2 mm. Another advantage of using steel is that this material offers numerous possibilities for the realization of the joint, especially compared to the only tongue and groove wood permits. Here are some examples of the most common joint you can find on steel interlocking planks. Chevron joint is the simplest shape of joint for interlocking steel planks. Clip joint is one of the most common and resistant shape of joint. Lock joint unable to realize chained joint that can be asked by architects. And gutter joint is rarely resistant but not convenient. On this example, you see that a fake wood coating was applied to remind of the original inspiration of these profiles, wooden cladding planks. For commercial building like this one, the first look is really important to get consumers inside. Here, this first image is upgraded by the use of interlocking planks compared to traditional trapezoidal or corrugated sheeting. Here is an example of what Bacacier done on a hospital. Another advantage of using steel cladding systems is that they easily allow you to implement solutions for exterior thermal insulation. These solutions are good to get a better use of the insulation, whether this is on new buildings or on existing ones. On this photo, you may see the architect chose to use corrugated sheets near the windows to rhythm the facade. This picture shows that interlocking planks can also be used on curved facade. The only limit to the use of these profiles is your imagination. On these examples, we only saw non-industrial buildings applications. Once again, these profiles are used on buildings that need to present a premium image to consumers or to the public. Here is the state of the art regarding the various design methods that were, before GRISP project, used in different countries. Both design by calculation and by testing existed. In some countries, only one of these methods was allowed to evaluate the performances of interlocking planks regarding wind loads, when others considered the two methods as suitable. During the redaction of Eurocode 3 Part 1.3, these profiles were not included in its scope. Therefore, before GRISP and GRISP Plus project, no harmonized solution existed at a European level to value their resistance, whether this is by calculation or by tests. The tests could be performed in a vacuum chamber or using timber blocks to apply punctual loads with various repartitions depending on the country in which they were performed. Under suction loads, a typical failure mode occurs for interlocking planks. Indeed, since only one edge of the joint is fixed, the free edge gradually go out of the joint, resulting in the dislocation of this last. This behavior is the most common when tests are performed using timber blocks, even when the span is not so important. We will see that it is not so obvious when tests are performed in a vacuum chamber. Now, we are going to see what tests were carried out during GRISP project and what were the results we used to develop the design method that will be presented thereafter. Two different profiles were tested within GRISP project. The first one is Cladeo 300 from Bacacier. This profile has a useful width of 300 mm for a height of 30 mm. All the tests were performed in two different thicknesses, 0.75 and 1 mm. The other profile tested was Zephyr 300 from Joricide. You can see that this profile has the same dimensions as Cladeo 300. The only difference between the two profiles is the shape of the joint. Clip joint for Cladeo and chevron shape joint for Zephyr. These profiles were chosen because they are the most common on the market and because they have the same dimensions. Once again, all the tests on this profile were performed in both 0.75 and 1 mm thicknesses. Flexion tests were realized in a vacuum chamber as allowed by Annex A of Eurocode 3 Part 1.3. They were performed and analyzed according to this document. For each test, 5 planks were assembled. You see the sensors that measured both vertical and horizontal displacement. These measures were done on the central plank. Horizontal displacement was only measured for suction tests. The aim of these measures was to get a better understanding of the dislocation of the joint. Due to the plastic foil needed to airproof the vacuum chamber, the results were unusable. We will see later that we found an analytic way to evaluate this phenomenon. Another important point is that support reactions were measured by load cells. Here's the test program for flexion tests performed on both Cladeo and Zephyr profiles in both 0.75 and 1 mm thicknesses. You also see that both pressure and suction tests were performed. This program was, of course, established according to Annex A of Eurocode 3.13, and the number of tests was chosen not to get a too penalizing statistical effect on characteristic values. The aim of these tests was to develop formulas to get the characteristic moment resistance by calculation. Here is an example of failure by local buckling of the flat flange in midspan under pressure loads. This is the typical failure mode we observed for these tests. On this picture, the sample was set up in single span configuration. On this picture, the failure of a double span sample under pressure loads is shown. Once again, the failure occurred by local buckling of the flat flange in midspan. For pressure tests on double span configuration with a distance between supports of 1 meter and 1 millimeter thick profiles, the maximum capacity of the vacuum chamber was reached without failure of the samples. You see here that interlocking planks can handle a great deformability before failure. One of the most surprising behavior we observed during suction tests was the failure of the samples. Indeed, as you can see here, failure occurred by local buckling of the compressed flange, the narrow one in this case, and not by dislocation of the joint. As you see here, the same behavior was observed for some of the double span tests. This result was surprising because this is a behavior that almost never occurs when tests are performed using timber blocks and not in a vacuum chamber. This means that when performances are evaluated on the basis of tests carried out using timber blocks, they may be underestimated. Indeed, wind loads are uniform loads, and performing tests in a vacuum chamber is a more realistic way to simulate these loads than to apply local loads by use of timber blocks. Even if some samples failed by local buckling of the joint, you see now that failure by dislocation occurred on other samples when the load applied was too important. On this picture, you see another example of failure by dislocation. We will see later how the maximum bearable load before dislocation can be determined thanks to an analytic approach. The other surprising result was the behavior observed during double span tests. Here is what the material resistance theory tells us about how the loads should be split between the different supports. We are expecting a central support reaction about 3 times the one we have on both end supports. Here is the behavior we observe when we have a close look to the reaction measures. The central support is acting like a hinge, and the profile is behaving like 2 different isostatic beams. Indeed, the central support reaction measure is about twice the reaction on both end supports, while theory tells us it should be more than 3 times. End support tests were also realized to see if the actual formula given by Eurocode 3.13 can be used for interlocking planks. You see here the setup of these tests. 3 assembled planks were tested according to Annex A of Eurocode 3.13. The test program given here is the one that was performed for both Cladeo and Zephyr profiles in both 0.75 and 1 mm thicknesses. Only one span was tested with 2 different cantilever lengths to see if this parameter has an effect. The results show no difference between the 2 configurations. Here you see a typical failure by shear effect on Zephyr profile, that is to say on a chevron-shaped joint. The same failure occurred for Cladeo, for clip joint. For some tests, as you may see on this upward view, failure occurred by flexion effects. You see on this transversal view that when failure occurs by flexion effects, no deformation of the joint can be observed. Even if interlocking planks are not included in the actual scope of Eurocode 3 Part 1.3, a type of profile sheets close to them is liner trays. Indeed, as liner trays, interlocking planks can be described as channel-type profiles with 2 narrow flanges, 2 webs, and 1 wide flange. But, as seen before, interlocking planks are sensitive to a particular failure mode for which no formula is given: dislocation of the joint. Therefore, we developed a theoretical approach based on the evaluation of the displacement of the joint and the limitation of this one. Here are given the notations used in the following formulas for the 2 most common shapes of interlocking planks: chevron-shaped joints and clip joint planks. These are the 2 profiles we tested and we included in the amendment proposal we submitted to European Commission. To apply the following method, the profile dimensions have to be in the following range. We will now see how to evaluate the moment resistance of such profiles. As the method is based on the one developed in Eurocode 3 Part 1.3 for liner trays performances evaluation, we have to determine 2 different moment resistances, one for pressure loads and one for suction loads. Under weak pressure loads, the wide flange is compressed. Therefore, we use Eurocode 3 Part 1.5 to determine the effective part of the wide flange, taking into account it is uniformly compressed and an eternal element. Regarding local buckling effect, we thus have to evaluate the slenderness of this flange and deduct the effective width of it. Taking this effective width, we determine the centroid position. Based on the previous centroid position, we then can determine the effective part of the web applying Eurocode 3 Part 1.5. This time, web has to be considered as an internal element with a non-uniform stress distribution. After the determination of the slenderness of the web, we can estimate the effective height of the compressed part of the web. We eventually can deduct the position of the centroid for the effective section, taking into account every effective part calculated above. Based on this centroid position, we evaluate the inertia of this effective section to determine the flexion modulus and conclude on the moment resistant performance, taking into account that the maximum admissible stress in the section is 80% of the material yield strength according to actual version of Eurocode 3 Part 1.3. Under suction loads, the wide flange is in tension. Eurocode 3 Part 1.3 says we have to calculate an effective width for this flange to take into account specific shear lag effects. To do so, we first have to determine the position of the gross cross-section of the profile E0. Based on this value, we can deduct effective width of the wide flange. After evaluating the effective width of the wide flange, the second step is to determine the effective width of the narrow flanges according to Eurocode 3 Part 1.5. They have to be considered as outstanding uniformly compressed elements. Based on the slenderness of these elements, we find their effective width and can deduct the centroid of the section considering both wide and narrow flanges' effective width. As before, we can calculate the effective part of the compressed part of the web according to Eurocode 3 Part 1.5, considering it as an internal element with a non-uniform stress distribution. Of course, compressed part of the web is, in this case, adjacent to the narrow flanges. Once again, we eventually can deduct the position of the centroid for the effective section, taking into account every effective part calculated above. Based on this centroid position, we evaluate the inertia of this effective section to determine the flexion modulus and conclude on the moment resistance performance, taking into account that the maximum admissible stress in the section is 80% of the material yield strength according to actual version of Eurocode 3 Part 1.3. For the determination of the end support reaction resistance, the actual Eurocode 3 Part 1.3 formula can be applied. The alpha value has been calibrated according to end support test results. Based on the behavior observed during double span flexion tests, no interaction moment local load has to be considered. To evaluate the maximum bearable load before dislocation, we determine the displacement of the joint based on an analytic method. This displacement is divided into 3 different components, 1 vertical and 2 horizontal. The first one is the vertical displacement in midspan of the fixed narrow flange, considering it as an embedded beam with a vertical load applied on its 3 extremities. Based on this model and on the inertia of a plate element, we can calculate this vertical displacement using the following formula. The first horizontal component to this displacement is the one resulting from the local deformation of the joint. To evaluate it, we consider the joint as an embedded beam to which a torque is applied on its extremity. Once again, the inertia used in the formula is the one of a plate element. The final component of this displacement, and the last horizontal one, is the one considering the bending of the wide flange and conservation of the angles between the webs and the wide flange. Once again, the inertia used in the formula is the one of a plate element. To deduct the total displacement, we superpose each of the 3 components determined above. The link between the local load U used in the previous formulas and the uniform wind load Q is given there. Eventually, we conclude to the maximum bearable load, limiting the displacement of the joint according to the shape of this one. Thank you for listening to this lecture, and I hope you enjoyed it. Goodbye.